Now, one of the things that we need to talk about now is something called significant figures. It is very, very important in the natural sciences, chemistry especially, that if you're going to report measurements and you are going to give someone data, that it has to be there has to be a certain degree of certainty associated with it. You cannot claim something that is not true. For example, if you take a measurement and say that the age of this thing is 8.765243 years old, that's a big difference in saying it's around 8 years old. One is far more precise and far more certain than the other. So, you got to be careful, and you got to make sure that if you're using instrumentation in the lab and that kind of stuff, that you recognize the limitations of the instruments that you're using, and you carry that over into the math, and you show that to me whenever you're doing the work. Okay, so this is all about writing numbers to reflect precision. Now, I want to point out the difference between exact numbers and actual measurements. Now, the only thing that significant figures, the only time it's going to be important and the only time it's going to weigh into what you're doing is if it's some sort of measurement that has either been taken by someone else or taken by you. Not just a definition of something or like a normal whole number or something. For example, what I mean is, if I asked you to tell me how many pennies were there, you'd say 7, right? 7 is, there's no need to get more certain on it. You don't need to say 7.0000 pennies because there's not 7.1, there's not 6.5, there's 7 whole pennies there. So by definition, we don't have to worry about that. That's not really what we'd say a measurement. It's more like just an observation that we can make. However, if we employ instrumentation and use some sort of tool to measure something, that's when we have to worry about our certainty and worry about the claims that we are actually making. Okay? Also, if you see a definition of something, for example, 1 ounce is exactly 1/16 of a pound. That is an exact number. It's a definition. It's not a measurement. This is not based on a measurement. It's just something that someone has defined. I don't even know what else. A mile is 5,280 feet. Okay, that's a definition. That's sort of a pure number. There's no measurement there. However, like I said, when you use an instrument and we're going to measure it using some sort of standard, that's when we have to watch what we do. So let me show you what I mean. I want you to report measurements to me in the lab and on your homework according to report it according to certain rules that involve how certain you are allowed to be. We're going to use what's called significant figures to do that. Okay? What's important to note is, like, if you take this number, 45.872, what this number means to me and what it should mean to you in this class is that you're for certain that you have 45.87 something and that you have estimated this last digit. For example, say you're using a balance, a scale, and you put your sample on there and the scale reads to 3 decimal places and it's saying 45.87, and these all hold constant when you're putting that thing on there, but this one's constantly bouncing around or whatever. Or maybe the next one is bouncing around. But something after the 7 is bouncing around, okay? And you have to sort of guess that we've got a 2 here. It seems to hang on to like the longest, okay? So you're going to guess that last one and estimate it. And what this tells me is that you are absolutely certain of these first 4 because they're not changing. And you're guessing on the last one because that's the best guess that you can give. Okay? All right. And we think about a thermometer for a minute. Now, we're going to use digital thermometers, so you just got to write down what you see. Let's say you're using one of these traditional types of thermometers. How would you incorporate significant figures? In other words, how would you incorporate certainty? How far can you go and still make a reasonable claim that someone in the science community would validate in terms of what the temperature of this is? If this is 105, this is 100, 1, 2, 3, 4, we know that for certain that this temperature ranges between 103 and 104. That's what we know. So I can write 103 point something. Now it's a matter of what is that something that I can write after that. Well, you give it your best guess. Okay? In this case, you're not going to put 103.0 something because you don't have that type of instrumentation to do that. You can only go 1 past what you're allowed to see here. So if you're only going by 1s, that's this column right here, right? 1s. You can only go 1 more past that because that's now where you can't see. So if we're at 103, between 103 and 104, then we got to eyeball it and we got to look and see. What does it look like? Well, if you sort of divide it in your head, you can see it's about halfway between 103 and 104, so you write 103.5, and that's how you would write that down. You wouldn't just write 103. You would actually write 103.5. If it was 1/3 of the way up, 103.3. Just got to get as close as you can given the circumstances. Okay? That's just telling you how you're going to read the instruments that you use in lab, how far you're going to take your measurements, that kind of stuff. Okay? Okay, now, this is where it gets tricky. We're all about coming up with numbers that reflect how certain we are about our measurements. That's the catchword for the day, certain. So what we have to do now is evaluate what digits do I see in front of me that actually contribute to the certainty that I'm trying to study here. What numbers do I see that are part of my measurement? I'll show you what I mean. What you're going to find is that obviously any number, 1 through 9, any of those whole numbers, or any numbers that you see, is obviously going to be important in your measurement, right? The only problem that you're going to run into is, in some cases, you're going to see zeros within this thing that you write at some point that may or may not actually be significant in terms of expressing certainty in your measurement. Some of them are very significant, okay? Now it's a matter of deciding which zeros are and which ones aren't. That's the only problem that we have. That's the only number, so to speak. Of course, zeros is not really, it's a lack of a number, right? Lack of value. That's the only situation that we're going to have where it's going to be a little bit of a problem. So let me show you what I mean. Okay? Notice this, though. I say that significant figures tell us the range of values to expect for repeated measurements. What that means is, if you say that the temperature is 103.5, that means it's probably going to, all I can say for sure is it's somewhere between 103.4, 103.6, something like that. Okay? Like on the back, think back to the slide I used with degrees Celsius. I said the global temperature increased about 0.6 degrees Celsius. What does that mean? It means it's somewhere between 0.5 and 0.7. I've got a window now that I've created. The more significant figures that I have, the more certain that I am, the smaller that window becomes. And I start honing in on what the true value actually is, and I have less variance from that. The window becomes much smaller. That's what we're striving for. That's what we want. We want to get as many sig figs as we can and as small a window of certainty as we possibly can. Okay? So that's why this is very important. Let's take a look at this measurement, 12.3 centimeters. How many of those figures, of those digits that you see, are significant in terms of expressing how certain that is? Well, don't think too hard about it. All of them are important. Okay? You have to have all those numbers to make up this number. That tells me that the range, think about it in terms of that. Okay? What numbers contribute to making the range, to defining the boundaries of this window? All of these do, right? It has 3 sig figs. We know that its range is from 12.2 to 12.4, somewhere in there. If I would have 12.34, I've narrowed my range. I've increased the number of sig figs, and I would actually go from 3 to 4 because all of those are contributing to the narrowing of that range, expressing certainty. So 12.30 has 4 sig figs. This 0 adds certainty. If I take it away, 12.3, my window is 12.2 to 12.4. With that 0 there, look how much more I've narrowed my window down, right? So I've become more certain. It actually has 4 significant figures as written. All right, so how do you figure out how many sig figs are present? It's not just how many spaces are taken up, how many digits are written there. It's actually a little more complicated than that, but it's not too bad. The number 1.5, for example, has 2 significant figures. That's an easy one. 1.05 has 3 significant figures. Anytime a 0 is between any actual numbers, this is obviously always significant. This number is always going to be significant. So that means if it's sandwiched in between 2 significant things, it has to be significant. That's the way it works. Okay? So there's 3 sig figs in 1.05. Trailing zeros after a decimal point. If I put more zeros on this, do I narrow my window? If I put more zeros this way, if I change it from 1.050 to 1.0500, am I increasing my certainty? I am. That's more specific, right? As opposed to just 1 0 after the 5. right here, my range would be from 1.049 to 1.051, right? What if I wrote this 1.0500? Notice now that I've made my range an even smaller number. I've narrowed it down even farther. This is more specific the more zeros I add after this number. Okay? So, as written right now, that 0 is important in expressing my certainty, because by adding it there, I show you not only am I sure about this number, but I'm sure about the next number. Okay? I'm narrowing my range. All right, so there's 4 sig figs there. So there's 2 here, 3 here, 4 there.